Hello everyone, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narola Institute of Technology. My today's subject is power system, and the topic of discussion is the concept on GMD and GMR of overhead transmission line. So this is the lesson plan of this particular subject. Here the subject name is electrical power system and subject code E502. This for BTech 5th semester students. And this is the course outcome of this particular subject. It has three CO, CO1, CO2 and CO3. Now I'm going to the main topic. So today I'm going to discuss on the concept of GMD and GMR. We will try to understand what is GMR and what is GMD and how to calculate GMD and GMR from a overhead transmission line or overhead conductors. So first I'm going to talk about the GMR, that is the geometric mean radius. So here the expression, the equation, we already defined this equation when we define single phase two wire line. That means at the time of inductance calculation of single phase two wire line, and also at the time of calculation of the inductance of three phase overhead line, we find this equation, that is the inductance LA. A means we consider conductor A. So if we consider there is a conductor and the conductor is A and the inductance of the conductor, the equation will be equals to LA equals to 10 to the power minus 7 into 1 by 2 plus 2 log D by R to the base E. And here the unit is Henry per meter. Now we have to modify slightly this equation. So how to modify? So look, in the second step of this calculation, here we take 2 into 10 to the power minus 7. That means inside the third bracket there was 1 by 4. Now if 2 is at the outside of the bracket, that means 2 into 10 to the minus 7 into 1 by 4 plus 2 is multiplied with log. So here it will be log D by R to the base E. That means 2 is a common part from the equation. So here finally we get in the third line that it is 2 into 10 to the minus 7. Now 1 by 4 we modified these as log e to the power 1 by 4 to the base E, because we know that it's a formula of logarithm that log e to the power m to the base E, that means it is equals to m, because log e base E equals to 1. So we can write 1 by 4 very easily, log e to the power 1 by 4 to the base E plus log d by R to the base E. Now LA equals to 2 into 10 to the minus 7 log d by R e to the power minus 1 by 4. It is also very simple formula of logarithm. So as per that, we know that if 2 logarithm is multiplied, that means log m plus log n, we know that we can represent it log mn. And then log m minus log n, we can represent log m by n. So here, actually the equation is d e to the power 1 by 4 by r. So we change e to the power 1 by 4 from numerator to denominator. So that's why it is d by r e to the power minus 1 by 4. Now, if we consider that r, the part of denominator with the logarithm, this is r e to the power minus 1 by 4, if we consider it as a prime, then we can rewrite the same equation like equation number 1. That means L equals to 2 into 10 to the minus 7 log d by r prime to the base E, Henry per meter. So we considering here equation, it is equation 1. That means we are considering r e to the power 1 by 4 equals to r prime. Now, why we are considering this? Look, the radius r prime is that of a fictitious conductor assumed to have no internal flux. But with the same inductance as the actual conductor of radius r. So the quantity e to the power minus 1 by 4, after calculating, we find it is equals to 0.7788. So that we can say that r prime equals to 0.7788 r, because e to the power minus 1 by 4 equals to 0.7788. So this term, this particular term r prime equals to r e to the power minus 1 by 4 is called geometric mean radius. That means this is GMR of the wire. So what is GMR? It is written in the first line. The GMR is that of a fictitious conductor assumed to have no internal flux. That means it's a particular area of the conductor up to some radius. There is assumed to have there is no internal flux, but with the same inductance as the actual conductor of R. So that part, or you can say up to that radius is called geometric mean radius, GMR of the wire. Now we are moving towards GMD. So GMD is geometrical mean distance. The full form of GMD is geometrical mean distance. Now we find that there are two types of GMD. One is self GMD and second one is mutual GMD. Okay. So the use of self GMD and mutual GMD simplifies the inductance calculation. Look how it simplifies. In last 3 lectures, we go through that how to find the inductance of a single phase 2-well line, how to find the inductance of a 3-phase overhead line, both for symmetrical and unsymmetrical spacing. So we know a method. We already discussed some method to find the inductance of a overhead line, single phase or 3-phase lines. So there, for calculating that inductance, first we measure the flux linkage of the conductor, the internal flux linkage, the external flux linkage of the conductor. So the calculation is slightly complex, but if we use this self GMD and mutual GMD, this self and mutual GMD is very significant for simplifies the inductance calculation. So we have to remember this part. So why we are going to implement or going to learn this method, because it will help us to find the inductance of single phase and 3-phase line. We can calculate using this method. We can calculate the inductance easily. Now the symbols used for these are respectively ds and dm. That means self inductance will be represented with ds and mutual inductance will be represented by dm. Now let's talk about self GMD. Look, let me explain first. Self GMD is nothing but GMR. Just try to understand this. We already know that last slide that self GMD is represented with ds. Okay. In order to have concept of self GMD, also sometimes called geometrical mean radius, GMR. So self GMD is sometimes called GMR. So consider the expression of the inductance per conductor per meter already derived. Inductance per conductor per meter equals to 2 into 10 to the minus 7 into 1 by 4 log d by r to the base z. If we simplify this equation, so it will be 2 into 10 to the minus 7 into 1 by 4 plus 2 into 10 to the minus 7 log d by r. We consider it for the self GMD equation number 1. Now look, in equation 1, the term 2 into 10 to the minus 7 into 1 by 4 is the inductance due to flux within the solid conductor. So the first part of the equation number 2 into 10 to the minus 7 into 1 by 4. So what is this? The term 2 into 10 to the minus 7 into 1 by 4 is the inductance due to flux within the solid conductor. For this purposes, it is desirable to eliminate this term by introduction of concept called self GMD or GMR, because we know that self GMD and GMR is same. So the self GMD or GMR is equals to 0.7788 R. Using self GMD, equation 1 becomes inductance per conductor per meter is equals to 2 into 10 to the minus 7 into log D by S. 2 into 10 to the minus 7 from equation 1, 2 into 10 to the minus 7 log D by R. So here it is going to converting to D by S. So what is DS? DS is nothing but GMR. That is the self GMD. So that will be equals to 0.7788 R. Now let's move to mutual GMD. Mutual GMD between two conductors is equal to the distance between their centers. Look, the term we have to remember, that is mutual GMD between two conductors is equal to the distance between their centers. So it is nothing but the distance between their center to center distance. That GM is equals to spacing between conductors equals to D if we consider the distance is D. So it is D. This is first point, and for second point, for a single circuit three-phase line, the mutual GMD is equal to the equivalent equilateral spacing. That is, look, this is for single circuit three-phase line. It is not double circuit three-phase line. That means only one circuit of red, yellow, blue will be there. That is the single circuit three-phase line. The mutual GMD is equal to the equivalent equilateral spacing. We find this term when we calculate the inductance for a three-phase overhead line when it was unsymmetrical spacing. So this term we already explained on the previous lecture. What is equivalent equilateral spacing? So for three-phase line, single circuit three-phase line, the mutual GMD is equal to the equivalent equilateral spacing, that is D1, D2, D3, D power 1 by 3. So for this case, we can say that the mutual GMD for a single circuit three-phase line is D1, D2, D3 to the power 1 by 3. Next, go to the third part, that is, if it is a double circuit three-phase line or three-phase double circuit line, then how to calculate the mutual GMD? So the figure is showing that it is a double circuit three-phase line with A, B, C, and C dash, B dash, A dash is there. So consider the conductor arrangement of the double circuit shown in the below figure. Suppose the radius of each conductor is R. Very significant. So here considering all the radius of all the conductor is same. And we already know that self GMD of a conductor is equals to the GMR, that is 0.7788 R. So self GMD of combination A dash is, so here you have to find the self GMD of combination A dash. So what will be the combination if we consider the self GMD between A dash is DS1? Then how many way we can arrange these A and A dash? We can arrange these A and A dash in four different ways. So what is that four different way? A dash, A dash, A dash, and A dash A. So this is the four different way we can arrange the two conductor A dash. So how many times? It is 1 by 4 times. 4 times. That means the equation is ds1 equals to d a into d a dash into d a dash into d a dash a to the power 1 by 4. Now the same way, with the help of same procedure, we can find the self GMD. Self GMD for combination BB dash. BB dash. So this is same. If we consider this is DS2, then DBB, d b b dash into d b dash b dash into d b dash b to the power 1 by 4. Similarly, ds3 equals to dcc into dcc dash into d c dash c dash into d c dash c to the power 1 by 4. So now we have to find the equivalent self GMD of one phase. So ds, if we consider the equivalent self GMD of one phase is ds, so how many phase? 3 phase. So it is ds1 into ds2 into ds3 to the power 1 by 3, because 3 phase is there, 3 combination is there. So this way we can find the mutual GMD of the conductor. The value of ds is the same for all the phases, as each conductor has the same radius. Now we are going to find the mutual GMD. So this is the procedure to find the self GMD of double circuit line, and this is for mutual GMD. So mutual GMD between phase A and B, suppose if we consider two phases, A and B phases. So look, in this figure, self GMD between A dash, self GMD between B and B dash, and self GMD between C and C dash. But for mutual, we have three combination, AB, AC, and BA, BC. So how many conductor is there? 3 A, B, C. So as per that, we have to find there is 4 combination for in between two conductor. So mutual GMD between phase A and B. So what will be that? This is same like the previous one. This is DAB, AB dash. That means how many way we can arrange these A and B phases. So 4 way we can arrange it: AB, A dash B dash, AB dash, and A dash B to the power 1 by 4. So what will be the value? What will be the mutual GMD between B and C? It is same like the previous one, BC. DBC equals to DBC into BC dash into B dash C into B dash C dash to the power 1 by 4. Similarly, between CA, it is CA into CA dash into C dash A into C dash A dash. Now finally, we have to find the equivalent mutual GMD. So this is, if we consider it is DM, we already defined that it is DM, the mutual GMD. So this will be DAB into DBC into DCA, already find it, to the power, how many combination? 3. So it should be 1 by 3. So in this way, we can find the mutual GMD for a double circuit line. So now at the end, we can say that the mutual GMD depends upon only the spacing and is substantially independent of the extra size, shape, and orientation of the conductor. So to make PPT, I take help from the book Principle of Power Systems by V.K. Mehta and Rohit Mehta. And thank you everyone.